All right, so I would say good morning, but I don't know when you're watching this, so good whatever day it is to you, whatever time of day it is to you. So first thing that we have up here, today we are talking about section 3.1, the derivative of a function. You are going to learn what a derivative is. This is a massively huge part of calculus. You need to know how to calculate a derivative. So the derivative is actually the proper name to what the book has previously called the slope of a curve. So we're going to flip to page 99 and we are going to look at the definition of a derivative. Let me look here. There we go. So the derivative of the function f with respect to the variable x is the function f prime whose value at x, is f prime of x is equal to the limit as h approaches 0 of f of x plus h minus f of x all over h, provided the limit exists. So yeah, you're gonna have to know that. You should write that definition down in your notes and save it for always. In fact, it's so important to be able to calculate a derivative, we have actually two ways of doing it. We have the definition and we have the alternate definition. So the alternate definition, the derivative of a function f at the point x equals a, is the limit f prime of a is equal to the limit as x approaches a of f of x minus f of a over x minus a, provided the limit exists. Now this big part down here where it says provided the limit exists, we talk about that tomorrow when we talk about differentiability. So right now we are just going to be calculating derivatives using the limit definition. Again, alternate definition is going to be important. I would suggest putting it in your notes because they're both important. Unfortunately, I can't really tell you which one you should use. It's really just a matter of practice that you figure out which one's going to be better. All right? So here we go. I guess it'd be useful if I told you guys the notation, all of these different ways of reading the things. I'm teaching you a new operation, so you have to know how to read it, how to say it. A couple of the things that we have, I was reading this notation for you guys already. It's called prime notation. That apostrophe right there in math is just read prime. So we would read this statement as f prime of x. Or you could call it the derivative of f with respect to x. If you define your function just as y, like we just say y equals or something like that, you can have y prime, all right? This one right here is called Leibniz notation. When calculus was invented, there were two guys that that really discovered it, and one of them, his name was Leibniz, and he used this notation to describe the derivative of y with respect to x. Nobody reads it as the derivative of y with respect to x. We would read this as dy dx. Don't read it as dy over dx, it is dy dx. And you can have df dx if we have the function defined as f, or the derivative of f with respect to x. Nobody really reads that except in very limited circumstances, like occasionally I will read it like that, but not often. And then over here we have d dx of f of x. And you can really put any function there, like you can say d dx of x squared or d dx of cosine of x, and you'll see that throughout the chapter. This is the notation that I prefer. Leibniz notation just allows us to understand things so much better. But I do have some really big cautions. By the way, you should probably put down how to read all that stuff. But these cautions right over here. One note. dx does not mean d times x. dy does not mean d times y. D is not a variable here. D is part of the operation, and it all comes down to the d dx kind of thing. Another caution we have here, dy dx does not mean dy divided by dx, except when it's convenient to think of it as division. df dx does not mean df divided by dx, except when it's convenient to think of it as division. And a final caution that I have for you guys, and then I'm going to show you why we use d dx, why Leibniz decided on this, because it's really quite brilliant why we use d dx in here. So note, d dx of f of x does not mean d dx times f of x, except when it's convenient for us to treat it that way. It means apply the operation of differentiation to f of x. So those cautions are important. Again, it's a new operation for you guys. It's easy to mess that stuff up, and I want to give you guys the cautions so that you don't mess it up. Now keep in mind a derivative is slope at a point. We happen to know that slope is equal to delta y over delta x. The derivative just means take that slope formula and make infinitesimal changes instead of finite changes in that delta. So what we look at here, when we switch from our finite differences to infinitesimal differences, that's when we change the Greek letter delta into the Latin letter d. dx. So that's why we use dy dx, and one of the reasons why I think personally that the ddx notation is just way cooler. It really drives home this huge concept that a derivative is slope at a point, and I cannot emphasize how important that is. It is massively, massively important. So let's get into it. I said let's get into it. Oh, yeah. Let's apply the definition to find f prime of x when f of x equals x cubed at x equals 2. Okay, so we're going to need to have a new page in here, and we are just going to take that first one. F of x equals x cubed at x equals 2. When you read something like that, I know in the notations that we had, f of x is equal to x cubed at x equals 2. I know in the book when we copied down the definitions of these, instead of saying the slope at x, we said slope at a. Oh, actually, in the original definition, it was at x equals 2. I'm going to do both definitions for you, because really it's just a matter of, you have to play with it to figure out which one is better. So here we have f of x equals x cubed. So what I can find here, f prime of 2. Using the standard definition. Remember the standard definition? The limit as h approaches 0 of f of x plus h minus f of x over h. And I completely copied that out of the book. I would encourage you guys to keep, referring back to the book and try to copy it down and make sure that you're getting it right. The only thing that I did between the book and my work was I changed the x to 2. All right? Let's go back here. Now I'm going to start applying all the stuff that I have up here to my definition. So I've got the limit as h approaches 0 of f of 2 plus h, so that would be 2 plus h to the cubed minus 2 to the cubed all over h. And we can try the direct substitution, but I will tell you, anytime you try direct substitution at this stage, you're going to get that 0 over 0. And just to demonstrate what I'm talking about here, I've got 2 plus 0 is 2. 2 cubed minus 2 cubed is 0 over 0. So we've got that indeterminate form. We really can't proceed right there. We have to just look for stuff that we can do. I hope at this point it's become clear that you have to you have to expand this binomial. It's up to you how you want to do it. You could FOIL out the 2 plus h and then multiply that 2 plus h, FOIL out the 2 plus h times 2 plus h and then multiply by 2 plus h again to get the expansion. But I think you guys saw this before. I like to use Pascal's triangle, and one of you did come in and ask me exactly how I use Pascal's triangle. So if you want to see that, come to office hours. I would be more than willing to show you, but at this point, that's not a calculus thing, expanding a binomial. So I see I've got 2 cubed plus 3 times 2 squared times h plus 3 times 2 h plus h cubed minus 2 cubed all over h. And that gobbledygook right there is just the expansion of 2 plus h cubed. I see I've got 2 cubed minus 2 cubed, crossity crossity, and now we've got the limit as h approaches 0. I hope I have enough room to write all this because there's a lot. Let's get rid of Pascal's triangle. I said, let's get rid of Pascal's triangle. So here I've got 3 times 2 squared, so 3 times 4, 12h plus 6h plus h cubed all over h. All right? So now I see in the numerator I've got all h's there. I now can do the limit as h approach 0 of factoring out an h times the quantity of 12 plus 6h plus h squared all over h, crossity, and now I can d sub. I've got 12 plus 6 times 0 plus 0 squared, which would equal 12 plus 0 plus 0, 12. I know that looks scary right now. I will tell you, legitimately, I'm going to scrub my mind of everything that I've done here, and I'm going to redo this problem real quick. So f prime of x is equal to 3x squared evaluated at x equals 2. 3 times 2 squared gives me 12. So after this chapter, that's how you're going to calculate a derivative. But before we get there, you don't know these rules yet, so you can't do that. That amount of work is the same as this amount of work. So this right here is the standard definition. That's one way of calculating a derivative. The other way to calculate it is using the alternate definition. And again, referencing back to that first week of class when I, whoopsies, not that one, when I saw you and I had that get to know you activity, some of you wrote that you liked math because there's always one answer, but more than one way to get that particular answer. So here, I can find, again, f prime of 2 is equal to the limit. And when we're using the alternate definition, we want to say the limit as x approaches whatever the value is up here. So in the alternate definition, when it says at x equals 2, that 2 value now becomes, that x value from up here becomes your a value down here. So it'd be the limit as x approaches 2 of f of x minus f of 2 over x minus 2. Now this is going to be a little bit shorter of work, but it's a little bit harder because of the factoring that we have to do here. We would have the limit as x approaches 2 of x cubed minus 2 cubed all over x minus 2. And I happen to know we have a difference of cubes here. So when we have the difference of cubes, we can factor that into limit as x approaches 2. I know x minus 2 is going to be able to factor out of that. After that, I know I'm going to have x squared plus, what was it, 4x plus 2, I believe. No, 4x plus 4. And I'm just checking that real quick. X cubed, then 4x squared minus 2x squared. No, that doesn't work. Oh man, I'm messing up horribly on how to factor this out. Is it that? I'm trying to think. X squared minus 2x squared, 4x and 4. Yeah, there we go. There we go. That's it. That's it. All right. All over x minus 2. And you can go back and FOIL that out to make sure that I factored it. Again, I find this one to be trickier just because the difference of cubes is a little bit harder to remember. Now, keep in mind, as long as we do this correctly, we should get the same answer. X minus 2 cancels out, x minus 2 cancels out. we have the limit as x approaches 2 of x squared plus 2x plus 4. If all goes well, we're going to have 12 off of this. Keep your fingers crossed. 2 squared plus 2 times 2 plus 4. Well, 4, 4, and 4 times 3 is going to give us 12. Whew, man. I will note that the alternate definition shows less work. It is quicker as far as the writing is concerned. But remember, I faltered right here, and you might falter as well. Cool? You will never have to use both definitions except in the assignment attached to this section, just because I'm cruel to you. That's how we do. Let's do another one. Because really, the big meat of this section is being able to evaluate a derivative here. Let's look at this one. F of x. F of x is equal to the square root of x at x equals 4. All right, cool. So we've got f of x is equal to the square root of x at x equals 4. Again, two ways to do this. Standard definition. Standard definition will be f prime of 4 is equal to f of 4 plus h minus f of 4 all over h. All right? Now, personal preference, I like the standard definition. You guys can't see me motioning. I like the standard definition better. It's just what I learned on, and I'm partial to what I learned on. So here, we're going to have f of 4 plus h. So the limit, ooh, man. Oh, man. I'm hating myself right here. I forgot the limit notation here. That makes this not make sense. Limit as h approaches 0 of the square root of 4 plus h minus the square root of 4, I think I know what that is, over h. All right? I did show you guys how to solve this type of problem last chapter. So here we have the limit. Let's just find out what square root of 4 is. Limit as h approaches 0 of square root of 4 plus h minus 2 over h. So this particular problem, in order to solve this, if you don't remember from last chapter, when I told you that on the solving limits section, I think the first section that we did in this book, you multiply by the conjugate. So square root of 4 plus h plus 2. Square root of 4 plus h plus 2. Now when I multiply by the conjugate, I now have difference of squares in the numerator. Difference of squares means I just have to do first and last. It's that a squared minus b squared that we have. So we've got the limit as h approach 0 first. So I've got square root of 4 plus h times square root of 4 plus h would give me 4 plus h minus 2 times 2 gives me 4 all over h times the quantity of square root of 4 plus h plus 2. Now, if you don't understand why I didn't distribute that h in the denominator, well, look forward a couple steps and you might be able to figure it out. And if you still can't figure it out, don't worry, it's coming up here in just like 1 second. 4 minus 4. Now look at that. H cancels out. We're left with the limit as h approach 0 of 1 over the square root of 4 plus h plus 2, and now I can d-sub. I now have 1 over the square root of 4 plus 0 plus 2. 4 plus 0 is 4 last time I checked. Square root of 4 is 2. 2 plus 2 gives me 4. The answer to this is 1/4. All right? There's the standard definition. In this particular problem, I know I said before that I tend to like the standard definition more than I like the alternate definition. This particular problem, my preference is for the alternate definition. So the alternate definition. It just pops out easier to me on this one. And I know I'm using subjective terms, and that's not really cool in math. We hate subjectivity in math. It is an objective course. but I'm old enough, I can have opinions. So again, I'm copying the alternate definition here. I would have f of x minus f of, remember, in the alternate definition, whatever it says, at x equals whatever, that's a equals whatever, over x minus 4. All right? So now I have, let's see, limit as x approaches 4 of the square root of x minus the square root of 4. I hope you guys are all right with me just putting that as 2, x minus 4. And if you can't figure out that it's 2, we did it right up here. See that? Yeah. Okay, cool. Oops. So now I could try direct substitution, and I would see that I'd get 2 minus 2 over 4 minus 4. So I'd get that 0 over 0. You're going to use the same strategy here, multiplying by the conjugate. I just happen to think that the conjugate's just a little bit friendlier in this case. And now I can see, multiplying by conjugate, I've got difference of squares. This is going to be the limit as x approaches 4 of square root of x times square root of x gives me x minus 2 times 2, 4 over, and just trust me, you don't want to do the FOIL in the bottom. If you can't figure out right now, just look at what I just wrote. If you FOILed it out, you'd have to refactor it to be able to cancel stuff out. So here, it just cancels right away. We have the limit as x approach 4 of 1 over the square root of x plus 2. And just again, verifying that we can do a problem 2 different ways and get the same answer both ways. So ultimately, if you are using the limit definition of a derivative, it does not matter which definition you use. Whether you use the standard definition or the alternate definition, you get the same answer. Long story short, nobody uses these. We use these to set up formulas for calculating derivatives, and then we very rarely use the limit definition. Shall we do, let's see. Let's go back here. Actually, I want to clear this page off and go back here. We're going to skip that third one because the third one is so similar to the first one, but the first one's a little bit harder. We're going to go to that fourth one real quick. F of x is equal to x minus 4 at x equals 0. Now, I do want to point out to you guys, there is a trick to this one. I'm not going to tell you the trick yet. Standard definition. F prime of 0 is equal to limit h approach 0 of f of 0 plus h minus f of 0 over h. And again, just copying that out of the book. You really want to write it down every single time because there's something about that tactile sensation of writing it that really drives it home in your head. So now we've got the limit as h approach 0 of f of 0 plus h would be 0 plus h minus 4 minus f of 0 is 0 minus 4 all over h. All right? Now I'm just going to start crossing. Negative minus negative, we get plus. Minus 4 plus 4, okay, those cross off. Zeros, we really don't even acknowledge their existence. We're left with the limit as h approaches 0 of h over h. This can't be right. H over h, h crosses. We're left with the limit as h approaches 0 of 1. Okay, constant in there, so the constant is the limit. Okay, it's just 1. Would you guys like the cheat now? F prime of 0 means just the slope of this function at 0. Look at this function. This function has a name. It is called a blank function. It is called I'm just going to say the name for you because we're not interacting because this is a video. It is called a linear function. Linear functions have a constant slope. You learned that in Algebra 1. What's the slope of this linear function? The slope of this function, because it's linear, is the derivative at all points on there. There's a rule for you guys. That's one of the rules that we have for calculating derivatives. Man, I know I told you guys that nobody in their right mind actually uses the limit definition to calculate slope, but I just find it fun to do. It's just a delight. You can see I got this one right. Got it right. There's the work for the third one if you really want to see it. Fourth one, we got that right. Ooh. All right, so again, the derivative is the slope of the original function. You have slope right here, rise is 2, run is 1, so we have a slope of 2. Connecting this, the graph of the original function to the graph of the derivative. Since the slope here is 2, we have the derivative will have a graph at 2. And the slope is constant because that little piece of the function has a constant slope, right? So look at here, we go from 2 to 0, we have a constant function for the slope. Down between 1 and 4, we have a rise of 1 and a run of 4. So writing the graph, we're going to draw the graph there at 1/4. Between 4 and 6, we have a rise of nothing and a run of 2. So the rise of a run there is going to be 0. Ooh, look at that right there, 0. And the rise here is -3, and the run is 3. So the rise over run there would be -1. Again, it's possible to graph derivatives to graph the derivative. It's not exactly the easiest thing in the world. Sometimes it gets kind of tricky, but you just have to play around with it. This link down here, I'll actually toss this link into Schoology for you guys to see it. But let me see if I can actually pull it up for you. I don't know if it's going to work. I know that link was broken last year. Oh yeah, I got it. I got it, guys. So let me pull it up right over here. It's an interactive graph showing differentiation of a polynomial function, which is just cool. And you can see right here, you can actually play around with it. Like we've got a quadratic function right here, where we have a negative slope right here. And as we go from left to right, that slope is becoming less and less negative. You actually look at it, it kind of like flattens out right there, right? And going over here, it's getting steeper and steeper. So there's where the derivative, we start out with a really big negative slope, and as we go to the right, it gets more and more positive. The derivative of that quadratic is going to look like a linear function. I know that, there's where it is. We can actually change this to a cubic, and we can see you have some positive slope right here, then you have some negative slope, then you have some positive slope right there. So that looking over to the derivative, right where the slope changes from positive to negative, we're going to have a 0 slope right there. Right where the slope changes from negative to positive, we're going to have a 0 slope as well. And you can see in between those two 0 slopes, the function goes down. That means the graph of the derivative has to be underneath the x-axis. Slope to the right or to the left of the first 0 slope, that's a positive slope. So we have to be above the x-axis. To the right of the second 0 slope, above the x-axis. I totally anticipate there will be massive questions on this tomorrow in class, so don't worry. I've got a wonderful worksheet. It's a matching activity. We're going to try to work on that, hopefully. Really, when I look at drawing the graphs of derivatives, I look for these 0 slopes, where we change from negative slope to positive slope. And that's where I plot all of my 0 derivatives, right? So a little bit less than -1, a little bit less than -1. A little bit more than 0, a little bit more than 0. At 3, sorry, no, not at 3, that's the 0. Down here is where I have the 0 slope. So a little bit after 2, which is right there. And then I just fill in with the positives and negatives. It's more of a fudge factor than a real art at this point, because you guys haven't really experienced derivatives. Transferring between the graph of the function and the graph of the derivative, it comes with practice, and we will practice it. All right. Here's again the same example that we had before. If we're looking at this, again, when I look at this, I try to find out where the slope changes from negative to positive, and that's right down here. So I have to have a 0 slope right there. Again, remember, this graph is the derivative. This graph right here is the derivative of this function. So it should show the slope at any point. In this part of the domain, we have negative slopes, so we show negative slopes down here. In this part of the domain, we have positive slopes. Again, it's going to take some playing around, and I think even this, the flip chart just references that we have some practice on derivative graphs. So we're going to do that in class because it's difficult, although the file is in the folder right now if you want to look at it. Actually, there's a couple files for derivative graphs in there. One-sided derivatives. One-sided derivatives are to find out if a function is differentiable. You test for, yeah, okay, so I can't talk right now. So it's for testing for differentiability of a function, which is going to come up in the next section. For a function to be differentiable at a point, the one-sided derivatives must be equal at that point. You can see I've got an example right down here. Show that the following function has a left and right-hand derivatives at x equals 0, but no derivative there. All right. So what we have is the left derivative. I'm just going to use the alternate definition. F prime of 0 is going to be equal to the limit as x approaches 0 of f of x minus f of 0 over x minus 0, or just x. Now looking at this, the left derivative is going to be this rule because we're to the left of 0. Limit as x approaches 0 of negative x minus 0 over x. Pay no attention to that 0. Negative x divided by x gives me -1. I know some of you are saying we could have just cheated. It's a linear function. The slope is -1. Yeah, whatever. I still wanted to practice with this. And plus, I just find it fun. Oh, man. I'm going to switch to here so you guys can see it a little bit better. You're not looking at the back of my overalls or anything. For the right derivative, we're going to have the exact same expressions right here. Limit as x approaches 0 of f of x minus f of 0 all over x minus 0. The one difference here, now the right derivative is going to be greater than or equal to 0, so it's going to be at that x. So this is going to be the limit as x approaches 0 of x minus 0 over x minus 0. Pay no attention to those zeros. This ends up being 1. So the left derivative is -1. The right derivative is +1. Keep in mind, a derivative is itself a limit. So for a limit to exist, the limit has to be the same from the left and the right. -1 and +1. Are they the same? No. So the derivative does not exist at this function. The function is non-differentiable at 0. It happens to be differentiable everywhere else, but not at 0. Again, next section, we'll talk about differentiability, and so this is the assignment we're going to be going over in class tomorrow. So yeah, if you have any questions before then, feel free to send me an email. Might not get back to you too quickly, but I might. So this was fun. Let's do this again sometimes, guys. Sometime.